Hello students, test. Let me start by playing this little introduction. Okay, that didn't walk. Well, okay. That didn't walk at all. So, that was intended to be a quick video, which would consist of me talking to you a little bit, even just showing you my surroundings. I'll be recording these at home. You'll be watching these at home. Happy social distancing season. I'm learning as I go how to do this and what best practices are. So, for now, I guess, let's just get well, no, let me say one thing first. I am going to post some homework associated to this lecture. The homework will be similar to previous homeworks. It'll be mostly problems from the book. Some differences are I will not collect it because I think, well, I agree with the assessment of the university that, rightly so, we shouldn't be collecting homework during the time when instruction is on hold, but I still do want to put these videos out. I'll take into account the fact that we've lost essentially 2 weeks of classes. I will. But for now, you know what? You can ask me logistical questions when we actually have a time that we can talk, and I'll try to set that up. It might not happen on Monday, day one, but it will happen. So let's start talking about logarithmic functions. And in order to talk about logarithmic functions, let's start by talking about exponential functions. You'll have to be even more forgiving of my inability to draw well because I'm on a tablet. So what do exponential functions look like? Well, there's the graph of 2 to the x, right? As x goes to the left, as x gets small, 2 to the x gets really close to 0, right? 2 to the negative a billion is basically 0. It's not quite 0. As x gets big, exponential functions grow exponentially fast, in the sense that they grow at a rate proportional with the number of them there are. And you've heard a few things about the exponential growth in the current pandemic, and that's kind of why we are where we are. Maybe I should compose, well, okay. That function, 2 to the x, take a look at it. Does it pass the vertical line test? So if you draw some vertical lines, yeah, all of those vertical lines, nope, that just checks that it's a function. It passes the vertical line test, so it's a function. Check the horizontal line test. All those horizontal lines cross the graph in at most 1 point. Some of them cross in 0 points, right? A line below 0 crosses it in 0 points. But that means that this is a one-to-one function. It has an inverse function. Let's graph its inverse function. So what things do we see going on in the original function? Well, we see as x when x is really close to negative infinity, y is really close to 0. So when x is really, really far to the left, y is basically 0. Let's flip that. That means that on the inverse function, when y is close to negative infinity, x is close to 0, but maybe I should emphasize it'll be positive. So let's go over here. That means I should see points down here where x is almost 0 and y is almost negative infinity. So there will be a vertical asymptote. Fair enough. What other things do we know about exponential functions? Well, I know what this point will be. Even though this is 2 to the x, for any exponential function, you'll see this point, x equals 0, y equals 1. So on the graph of the inverse, you'll see the point 1, 0. And then let's see, as x progresses, as x gets big, y gets big, and y gets big really, really fast. So you see this thing, it's carving upward. So it'll keep on growing, but instead of speeding up as it grows, it will slow down. So you'll see a logarithmic curve. So this is the graph of the inverse function of 2 to the x. And we'll give this thing a name. I will call that the log base 2 of x. Everyone happy so far? Well, you can't answer that. This isn't actually an in-person lecture. So, oh, hi, cat. Sorry, this is one of the reasons I wanted to include some video so you could see that my cats are afoot. And don't worry, you'll get to see my cats. So, logarithmic function with base b, written log base b, is the inverse function to b to the x. So this is the inverse, this thing is the inverse to 2 to the x. So it is the log base 2 of x. The book will say log base 2 log of x when it means log 10 of x. And that's a semi-standard convention. It's not completely 100% held. For instance, if you're a mathematician, like, say, Wolfram of Wolfram Alpha, your favorite base will be base e. So it's conventional to call that the natural logarithm, ln of x, for the French from log naturel, will be the log base e, where e is Euler's number. It has lots of special properties, which really come up in calculus. Some computer systems, like Wolfram Alpha, will assume that you mean log of x. Oops. We'll assume you mean the natural log of x when you write. Sorry, I think this is what I want to highlight. Yes. Some computer systems will write that. Will think you mean ln of x. And some others, though this is maybe a little bit less common, if you're a computer scientist, then your favorite base is base 2. Basically because computer scientists mostly just believe in the digits 1 and 0. So for a computer scientist, the log of x will mean the log base 2 of x. So if you're going to use a computer and you want to just write log of x, make sure you know which base you're in. So let's unpackage this a little bit. So occasionally, let's think about what expressions, sorry, the cats are being very distracting and I wish I could show you. Good job, cats. So let's think about what a logarithmic expression means. So when someone writes, sorry, let's jump right here. Someone writes y is equal to the log base b of x. Remember, log base b of x is the inverse function to the natural exponential. So that means the difference between log base b of x and the exponential function is just that the x's and y's will be switched. So y is equal to log base b of x means exactly the same thing as b to the y is equal to x. So I'm going to write that down maybe a little bit off to the side. Log base b of x equals y means b to the y is equal to x. And there are words for the two different forms. Something that looks like log base b of x is equal to y, I will say is in log form. Or if I want to be very formal, I'll say it's in logarithmic form. Something in the form b to the y is equal to x, I will say that is in exponential form. Cool. Yeah, I should have shut the cats out of this room. They're being very involved. They're not used to us being home, right? And I've also taken one of our guest rooms and converted it into a recording room. So that means I've taken the bed and put it on its side, and that's very new to the cats. Now they have a new space to explore. All right, so back to the task at hand. Let's think about translation between these. So these are all equations in exponential form. I see in this case, pi cubed is equal to m. So that's something where I see a base to an exponent is equal to, well, something on the other side. So let's rewrite that in logarithmic form. So the base will still be the base, but it'll be the base in a log. Log base b of m will be equal to the exponent, 3. So this thing on the other side of the equation will become the dependent variable, which, right, is what you expect. Inverse functions switch the role of independent variable, dependent variable. This m is the independent variable before. Nope, the dependent variable before. Now it will be the independent variable. This 3, if you like, is a variable that you're plugging in to the exponent of pi. Oh, god damn it. Sorry, this is part of the difficulty of learning by doing. Yes, erase, though. I want you to erase the b also. Okay. That b should be, oh, god damn it. The base is still the base. Okay, let's move along. E to the x is equal to 9. So I see an exponential equation. I see base to a power is equal to a number. So we can rewrite that as the log base e of 9 is equal to x. Ah, but you see this log base e, that's the same thing as ln, natural log of 9 equals x. X to the power of 4 is equal to 81. What is the base? The base is x. So that will become the log base x, the base is still the base, of 81 equals 4. People feel pretty good about that? Nice. We can go the other way too. We can translate from log form to exponential form, and these are both important things in different situations. After doing these, we'll decide for which of these was this a good thing to do. So let's start with the first one. Log base pi of 3 is equal to m. So I see there's the base. There's the thing on the other side of the equation, the dependent variable. So when we rewrite it in log form, it will become pi, the base is still the base, to the m. The thing that used to be on the right-hand side of the equation is now the thing in the exponent, equals 3. Fair enough. Next one, ln of x is equal to 9. So remember, this ln is log base e. So the base in that logarithm is e. So I can rewrite that in exponential form as e to the 9 equals x. And we can do the same thing in the next one. Log base x of 4 is equal to 81. Well, this x is the base, so it will become x to the thing on the right-hand side of the equation is equal to 4. Nice. So that's just converting an equation from one form to another. Let's suppose we had a goal in each of these. So let's suppose that for each of these we wanted to solve for the thing that's the variable in the equation. So let's suppose we wanted in this first one to solve for m. So if you look at this first one, did we make our lives better or worse by applying log form? Well, m was already solved for. Right, right, we already had the equation of the form number equals m. There. So, in this case, this was not helpful. All right, well, that happens sometimes. Let's think about the second one. E to the x is equal to 9. Suppose we wanted to solve that for x. Ah, well, here, this is something of the form x is equal to something. And you know what? There's one bit of shtick which I should have set this up in advance. I apologize for my oversight here. I am going to let's see, you know what? Let's use the Google calculator. So apparently, I solved this and got x is equal to the ln of 9. Let's get a decimal approximation for that. ln of 9. It's around 2.197. Oh no, oh no, 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 no. Oh dear. Okay. Oh gosh, 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 gosh. Let's pause this for a second. Okay, that was interesting. Anyway, we just computed the log base 9 of x. Unfortunately, I panicked and closed out of that browser window, so while you can see easily what that was by flashing back, I can't. Somewhere around 2.1. That's good enough for me. Let's think about this next one. Did this change help us or harm us in this case? Let's see, it's not already solved for x on this side, but it's also not already solved for x on the other side. So neither one is obviously better. But let's forget about the fact that this is a logarithmic lecture. If you wanted to solve that, what would you do? Well, you take the fourth root of both sides. You would say, well, x is actually equal to the fourth root of 81. I'm not, well, I know what the fourth root of 81 is. It's 3. Right, the square root of 81 is 9. The square root of 9 is 3. So fourth root of 81 is 3. So in this case, applying the log didn't help us. Putting this in log form was not helpful. Log form. So the one above, the log form, was definitely helpful. Log form not helpful. Let's go to the other side. Let's think about solving logarithmic equations. So this one on the left-hand side, well, it looks like it's just fine already. Right, we already have, m is already solved for. This translation to exponential form, putting in exponential form, sorry, that's the cats still, form, was not helpful. I promise that you will get to see them. Let's think about this next one. Was it helpful putting this equation into exponential form? Well, yeah, it was, right? If you wanted to solve for x, I don't know what x is right now, but on this side I have x is equal to e to the 9. So in this case, this says that we have now solved for x, which is useful. Nice. So let's try again. So I don't know what e to the 9 is approximately off the top of my head, and I have no way which does not use a computer of approximating it. So let's go ahead and do that same thing again. E raised to the 9. That is around 8,000, 81,003. So it's, come on, you can do this. Come on. This one has x approximately 8103. Cool. Let's think about this final one. The log base x of 4 is equal to 81. Well, let's see. This is definitely not solved for x. X is in the base. Over here, still not solved for x. But notice, does this look easier to solve for x? At least getting a formula for x? Yeah, it's x to the power 81 is equal to 4. You want to undo raising something to the power of 81, you take the 81st root. X is equal to the 81st root of 4, which, again, we can compute that. And remember, roots can be written in terms of fractional exponents. 1 divided by 81. So there's how to compute the 81st root of 4. What do we get? We get something that's around 1, which is not surprising. Is approximately, is approximately 1.02. Okay, well, the same thing isn't going sideways, so that's good. Nice. So, as we've seen, oftentimes it's hard to compute logs by hand, right? I don't know what the natural log of 9 is, for example. But sometimes you can compute logarithms by hand by just saying, well, I'm going to write down the exponential equation that this is modeled by, and I'm going to solve that. So let's try to do that. So if I wanted to evaluate the log base 4 of 32, well, here's a nice game. If you want to know what something is, sometimes it's useful to give it a name. So let's say the log base 4 of 32 is x. Let's just give that value a name. It has some value. Let's try to figure out what that value is. Oh, but wait. There's an equation that's in log form. I can walk with that. I can rewrite this in exponential form as 4 to the power x is equal to 32. And during the most recent lecture, which admittedly was a billion years ago, we developed a technique. All of these numbers, 4 is a power of 2, 32 is a power of 2, we can take advantage of that. So we can rewrite that as 2 to the 2, because 4 is 2 to the 2, x is equal to, well, what is 32 as a power of 2? Well, count your powers of 2. 2, 4, 8, 16, 32, 5. 2 to, which is, so 2 to the 2 to the x is equal to 2 to the 5th. But we can apply exponential laws to see that that's the same as 2 to the 2x is equal to 5. Exponential functions are 1 to 1, so I can, 2 to the 5. So I can undo the exponentiation. I can rewrite that as 2x equals 5. So x is equal to 5 over 2, or if you like, 2.5. That seemed pretty okay. Oh dear. I think that's about where I want this. Okay, let's try that same game again. Let's try to compute log base 5 of 625. And what I'm going to go ahead and encourage y'all to do is try to repeat this same thing on your own. So pause the video, do the computation on your own, come back, and then I'll talk through it. Okay, good. You did it. Let's go through the walk. Log base 5 is 625. Let's give it a name. It doesn't matter what name you give it. Maybe to be different from what's above, I will call it y. That's an equation in logarithmic form. I can rewrite it in exponential form as 625 is equal to 5 to the y. And, well, even if you don't know your powers of 5, from context you can probably tell this probably means that 625 is a power of 5. So even if you don't know what power of 5 it is, you can figure it out by just listing your powers of 5. So let's see, 5 times 5 is 25, times 5. Let's see, 5 times 5 is 5. 5 times 5 is 25, sorry. Okay, this is how I'm going to do my multiplication. 2 times 5 is 10. 125. So there's 5 to the power 3. Let's do it again. Multiply that by 5. 5 times 5 is 25. Carry the 2. 5 times 2 is 10. Becomes 12. Carry the 1. 5 times 1 is 5, but there's a 1 there, so it becomes 6. 625 is 5 to the power 4. Nice, so this becomes 5 to the power 4 is equal to 5 to the power y. But again, exponentiation with base 5 is 1 to 1. The only way 5 to the blah is equal to 5 to the blah is if those two blahs are the same. So I can rewrite that as 4 is equal to y, and I can write down my conclusion now. That means log base 5 of 625 equals 4. And you know what? We have access to a machine. Oh, yeah, I want this. We'll talk about how to use a device like this to compute logs with multiple bases, but it takes a bit of work and requires some knowledge that we will develop. But for now, let's just talk about how to walk with multiple bases. So you have your own calculator. Take a look at your manual. There's probably some way of walking with multiple bases. If you can't figure it out, shoot me an email. Also, you have access to Wolfram Alpha, so I'm about to show you. Log base, nope, that's the wrong one. I want the underscore. Base 5 of 625. It'll do what it do? Yeah. There's the result. It's 4. There's the 4. Nice. So, time management is very bad, but let's just keep on going. So, it's just some basic things about logarithmics. Why do we care about logarithmics? We care about logarithmics because they're what we need to solve exponential equations. Here are some equations. Let's solve them. We'll get exact solutions and approximate solutions. I'll bust out a computer in order to get the approximate solutions. So the first is a thing that we failed to solve on the first day we talked about exponentials. the previous lecture. Let's solve this equation. Let's solve 5 to the x is equal to 7. Well, that's an equation in exponential form. Sorry, I should do this. There's an equation in exponential form. So I can rewrite this in log form, and let's just see what it becomes. So there's the base. The base is 5. So this will become log base 5 of 7 equals x. Oh, hey, cool. That means there's the exact value of the solution. I've solved for x. Let's try to find the approximate value. Oh, god damn it. Okay, that'll do. Let's try to compute the log base, nope, base 5 of 7. And there's something that's being spoiled right here. Notice this, that observation that Wolfram Alpha tells you will be relevant in a future lecture. But for now, we just wanted the decimal approximation. There it is. It looks like we have a decimal approximation of somewhere around 1.21. Nice. Again. Let's try to solve the equation 3 to the x to the power 2 is equal to 8. So there are two different strategies one might use here. And, well, what's the philosophy of solving an equation? You solve an equation by taking everything that's on the side that has the x and trying to undo it, move it to the other side by applying its opposite. So let's do that. 3 to the x to the 2 is equal to 8. The first thing I see is this square. How do you undo square? Well, you square root. So you'll get 3 to the x is equal to plus or minus square root of 8. And let's meditate on this for a little bit. This is now two different equations. This is 3 to the x is equal to plus the square root of 8, and 3 to the x is equal to minus the square root of 8. But remember, exponentials can only ever be positive. The range of 3 to the x is the open interval from 0 to infinity. So the negative choice is not valid. The only option I have is the plus. So it looked like there were two equations, but there's really only one. And now, oh, check that out. That's an equation that is in exponential form. I can rewrite that as an exponential in log form. X is equal to the log, oh, hi cat, base 3 of the square root of 8. There's one solution technique. Another solution technique, well, if you want to solve an equation, sometimes it's helpful to simplify the equation before you solve it. We can do that. We know exponential laws. This is an x, so here's second proof technique. Oh, hi cat. 3 to the x to the 2, that's the same thing as 3 to the x times 2, or 2 times x, is equal to 8, by using a log law. Nope, an exponential law. We haven't learned any logarithmic laws. Well, that is now an equation that is in exponential form. I see a single base raised to a power is equal to a number. That's an exponential form. I can rewrite that as x times 2 is equal to the log base 3 of 8. Oh, nice. So that's basically done. So what do I get? I will get, just divide both sides by 2, right? x is equal to 1/2 log base 3 of 8. So one thing that you might notice is this answer does not look like that answer. That was by design. But whenever you do something two different ways and you get two different looking answers, that tells you either a mistake has been made, which is not the case this time, or it tells you that maybe there's something deeper going on. These two numbers have to be the same, but they look very different. That's going to hint towards that logs satisfy some algebraic rules. So let's check that these two things are the same. So let's compute the log base 3. Oh no. Alternate key. No. Sorry, you probably can't see that. Of the square root of 8, close parenthesis, enter. Again, we see like some simplification happening. Apparently that is somewhere around 0.95. Let's try the other option, which hopefully will give us the same value. Parenthesis, 1. Where's the divide by sign? Over 2, close parenthesis, times the log base 3 of 8. Yeah, we get the same decimal approximation, somewhere around 0.95. I could swear that I just wrote that, though. And remember that those two are the same. That's hinting at something that we will do later on. All right, well, fine. That's fine. Let's solve this next equation. 3 to the x squared is equal to 8. And there's also multiple ways to think about this, but so let's see, this is in exponential form. It's 3 to a power is equal to 8. So that will give me x squared is equal to the log base 3 of 8. And so it will result in, well, I guess I have to take the square root of both sides. X equals plus or minus the square root of the log base 3 of 8. And this is showing me a positive and a negative solution. And let's just think for a moment whether both are actually valid. And let's think about it by imagining if plugging that back into the formula. 3 to the x squared is equal to 8. Well, regardless of if I use the positive or the negative branch, the first thing I do is I square it. You square it, it becomes positive. And a positive number, yeah, that can show up in an exponential. Cool. Both solutions are valid. There are two solutions to this equation. Nice. Let's think about an application-driven example. So there are lots of things, population growth, for example, say the spread of a disease, to be maybe a little bit topical, which are modeled via exponential functions. So what we hit last time was a toy example coming from Star Trek, that a population of tribbles aboard the Enterprise, where you start with one tribble, is measured, is modeled by the formula population at time t is equal to 2 to the t. T is measured in hours. Let's suppose the ship, I don't know, Scotty, has done some computation, and found that the life support systems will be overwhelmed once the population of tribbles hits 30,000. How long does the crew have to solve the problem? Well, so, right, this is, the math is not going to be hard. It's just a matter of figuring out what it's asking. It's asking how long the crew has before the population hits 30,000 triples. So that means I need to know when will P of T equal to 30, nope, 30,000? Yeah, 30,000. And apparently I need to solve for T. And the 30,000 seems like a pretty big number, so maybe you expect that they'll have a fairly long amount of time. Let's try to solve it though. So P of T is 2 to the T. So it becomes 2 to the T is equal to 30,000. That's an exponential form. We can rewrite it in log form. T is equal to log base 2 of 30,000. Presumably we care about the size of that number, not just the formula for it. So let's try to compute what that is using a machine. Let's compute the log base, base 2 of 30,000. That seems like the right number of zeros. Yes. 14.9-ish. So it's approximately, 14.9 hours. And that is not very long. So there are two things that this is demonstrating. Exponential growth is fast. At this thing's rate of growth, it will reach 30,000 in 14 hours. That's pretty quick. The other thing this is telling you is logs grow slowly. 30,000 is pretty big, but when you plugged it into log base 2, it was not that big. Cool. So let's develop some more stuff about logs. So, trick question. Let's evaluate the log base 2 of -3, and let's use the tricks that we've been developing. So to evaluate log base 2 of 3, that means that I need to, I'll say something like log base 2 of -3. Let's give it a name. Let's call it x. So that will mean that 2 to the x is equal to -3. Oh, but there's a problem here. 2 to the x is never negative. So this has no solution. So there's no value for x that solves this equation. Oh, that means that log base 2 of -3 has no value. -3 is not in the domain. And in fact, no negative number will be. 0 won't be either. And to remember that, let's just even recall what the graph of log, well, there's the graph of the exponential function. So I guess this is 2 to the x. Its range is 0 to infinity. So that tells you something. That tells you that the domain of log base 2 of x is the same as the range of 2 to the x, so that should be 0 to infinity. The domain of the logarithmic function log base b of x is the interval from 0 to infinity. Next, let's try to evaluate log base 1 of 4. Something similarly bad will happen. So that, let's see, I'll rewrite that as log base 1 of 4 is equal to y, just because x was used above. Rewrite that in exponential form. I will get 4 equals 1 to the power of y. Wait, but 1 to the y is always equal to 1, so this equation is just 4 is equal to 1. But 4 is not equal to 1. This has no solution. So that means log base 1 of 4 does not exist. In fact, log base 1 of anything does not exist except for 1. But then you're solving 1 to the y is equal to 1, and that has everything as a solution, so log base 1 of 1 is everything. So the takeaway is the function log base b of x only makes sense when two things happen. B is greater than 0, and b is not equal to 1. So I'm going to write that in blue just to write this again. The only valid bases are positive. I won't allow a negative base. 1 is not a valid base. So I won't allow negative numbers in the base. I won't allow 0 in the base. I will not allow 1 in the base of a log. Nice. So, all right, let's keep on doing. So, let's talk about graphs of logarithmic functions. So we've already kind of seen, so there are two types of exponential functions. There's exponentials with positive base. Nope, not positive, greater than 1 base. You can never have a negative number in the base of an exponential. And, or at least if you want to think of it as the exponential function, I mean, negative 1 to the power 2 makes good sense, but negative 1 to the power pi does not. And there's the case that 0 is less than b is less than 1. So that's what logarithmic functions look like. That's what exponential functions look like. If I want to compute logarithmic functions, well, I just need to flip those over the line y equals x. And that's easy enough to do. We've already seen log base 2 of x. Any log will look the same. It'll have this vertical asymptote at 0 where it shoots to negative infinity. There will be this x-intercept at 1, 0, because these guys have a y-intercept at 0, 1. And the red graph, well, notice the red graph differs from the blue graph by it looks like flipping over the y-axis. So the inverse functions should differ by flipping over the x-axis. Okay, so it looks like my scaling is bad, but you'll have to forgive that a little bit. Let's think about domains and ranges. What are the domains of these? Domains of these logarithmic functions? Well, look at these. How do you compute domain? You draw a bunch of vertical lines, you decide which vertical lines intersect the graph. Looks like when x is negative, no, there are no intersections. When x is 0, there's a vertical asymptote, but it doesn't quite make it to the vertical asymptote. So 0 isn't in the domain. But everything positive is, so the domain of log base b of x is 0 to infinity. The range of log base b of x appears to be negative infinity to infinity. And you'll notice I will never allow a base of 1. I will never allow a negative. Well, I'll also never allow 0. And I'll never allow a negative. These things have x-intercepts at 1, 0. They have vertical asymptotes at x equal to 0, but the type of x-intercept depends on whether the base is positive or negative. And in fact, let's pay a little bit of attention to how the graphs of log base b of x change as b changes. And you can fill these out on your own. I think what I'm going to do is I will resort to, well, right, of course I'm going to use a computer for this. Let's graph Alright, so there are the things I want to graph. I will graph log base 2 of x. And you know what? I'm going to do something weird here. I'm going to pause. Alright, we're back. Cool. So I want to sketch the graph of log base 2 of x, log base e of x, so ln of x, log base 5 of x, and log base 10 of x. Wolfram Alpha is perfectly happy to take the real part. So it will tell you something slightly wrong. It makes it look like the domain is bigger than it is because it believes that the log of a negative will just be something complex. But let's take a look at the graphs. Oh, I can even trace these. So let's see. So the green one is the log base 10 of x. There it goes, and it comes up and it goes up like that. There's the log base 10 of x. The yellow one is the log base 5 of x. The red one is the log base e of x. You see Wolfram Alpha is perfectly happy saying that the log base e of x is the log of x. That's the convention it follows. There's the log base 2 of x. So you notice something here. As the base is getting bigger, all of the graphs look qualitatively the same, but it looks like as the base grows, the graphs are being compressed horizontally. And we will explain this fact. Oh no, I don't want any of those colors. As B grows, the graph compresses horizontally. Nice. Cool. So I'm going to try to fix something because something is... All right, and we're back. So the last few things I want to do is, so that's a sales pitch for the change of basis formula, the thing we just did. So let's find the domains and intercepts of some of these graphs. I won't try to actually graph them. Let's do it manually. So I want to find the domain of this function, log base 2 of 3x minus 4. So that means I want to solve the equation 3x minus 4 is bigger than 0. Why that? Well, what things can you plug into a log? I can plug positive things into a log, so the thing inside of these parentheses has to be bigger than 0. So there's the inequality I need to solve if I want to compute this domain. This is a very simple function. It's linear, so I can solve it the same way as I would solve an equality. I'll add 4 to both sides, and then I'll divide by 3. X is bigger than 4 over 3, so it looks like the domain is 4 over 3 onto infinity. Nice. Next, let's try to find the x-intercept. How do you find an x-intercept? Well, x-intercept is when y is 0. So to do that, I need to solve log base 2 of 3x minus 4 equals 0. And there's a general shortcut that you can see, but let's do this as an example of solving a logarithmic equation. So that's an equation in log form. I can rewrite it as an equation in exponential form and get 3x minus 4 equals 2 to the 0. Oh, but 2 to the 0, that means take 2 and multiply it. Don't multiply by it ever. So don't even multiply by it once. Anything to the power of 0 is always 1. So 3x minus 4 is equal to 1. Add 4 to both sides. 3x equals 5. X equals 5 over 3. So it looks like this thing has an x-intercept at 5 over 3. It's an x-intercept, so the y value should be 0. Nice. Let's repeat. Let's suppose we want to solve this equation. So first, there's no equation. Let's try to find the domain of this function. So domain. So to find the domain, the thing inside of the parentheses needs to be positive. So 4 minus x squared needs to be bigger than 0. Oh, but that also looks like a super easy equation to solve. So step 1, solve equality. So 4 minus x squared equals 0. Add the x squared to the other side. 4 equals x squared. Take the square root of both sides, but remember that you're going to get a plus or minus. So there are two solutions to equality. This is a, let's look at the original thing. This is a downward opening parabola. And I want to know when it's above 0. So, right, in some sense you can just now know what the answer is, but let's draw a picture. So there's the graph of 4 minus x squared. I want to know when it's positive. Looks like it's positive between the intercepts. So the domain is -2 to 2. Why am I excluding endpoints? I'm excluding endpoints because this was a strict inequality. Nice. So, continuing on, let's find the x-intercept. I acknowledge that you're probably running out of space if you printed out the notes, but you probably didn't print out the notes. I hope you have the notes in front of you, but I hope you're walking this out just on paper of some sort. X-intercept. So to find the x-intercept, I want to solve log base pi of 4 minus x squared equals 0. So, going through all the motions, this is an equation in log form. We write it in exponential form. 4 minus x squared is equal to pi to the 0. Oh, notice pi to the 0 is equal to 1. To find the x-intercept, it sure looks like it doesn't matter what the base is. So 4 minus x squared is equal to 1. Let's add x squared to the other side, subtract 1. So 3 equals x squared. Looks like I'm getting x is equal to plus or minus square root 3. Or root 3 comma 0. It's a point, so it should be written as a point. Negative root 3 comma 0. Nice. Cool. So, let's move along. Let's go to the next page. So, let's try to repeat this. And I think now I'm just going to start settling with just domain. So let's try to find the domain of this function. So in order to find the domain, I need to solve an inequality. I can only see a positive number inside of a log. So I need to solve 1 plus x divided by 1 minus x bigger than 0. And this is a rational function. So there's an extra step in finding these important points. So the first is set equal to 0. So first 1 plus x divided by 1 minus x equals 0. Multiply over the 1 minus x. Get 1 plus x equals 0. X is equal to negative 1. There's one of the important points that we need to care about. The next is the vertical asymptotes. And you remember how to find vertical asymptotes of rational functions. You just set the denominator equal to 0. 1 minus x equals 0. X equals 1. So those are the critical values that we need to check. And now we need to decide where this thing is positive and where it's negative. So I need to check between and beyond. So let's start with this. So there's the graph, there's -1, there's 1. So I think, right, so there are two options here. If I want to find, decide whether it's positive, bigger than 0 or less than 0 to the left of -1, I could plug in -2, or I could try to plug in -10 trillion. Plug in a really, really big negative number. This thing should, the value of the function should be close to the horizontal asymptote. So y should be close to the horizontal asymptote, but look at this function. It's a linear function divided by a linear function. Leading coefficient is 1. Leading coefficient is -1. So the horizontal asymptote is at -1. A number that is close to -1 is less than 0. So that tells you that all of those values to the left of -1 will result in output values for this rational function, which will be negative, which are the opposite of what we want. These will not be in the domain. We can do the same, well, I guess to the right, let's use the other strategy just to make sure we remember the other strategy. Let's plug in x equals 2. 1 plus 2 over 1 minus 2. That's positive, it happens to be positive 3, divided by a negative, it happens to be -1, but I don't care about that, I just care about that this is negative. So all of these values will be not in the domain. Let's try to plug in 0. When you plug in x equals 0, you'll get 1 over 1. Hey, yeah, that's positive. So these numbers between are good. Those are in the domain. So I know what the domain is now. It's the interval from -1 to 1. I need to exclude 1 because it's a vertical asymptote. I need to exclude -1 because I want to solve a strict inequality. Let's try to find the domain of the log base 1/2 of absolute x. Well, let's try to do it. It looks like then I need to figure out when is absolute x strictly bigger than 0. But remember the absolute value function. I can even just look at a graph to see this. There's the graph of the absolute value function. You'll have to excuse that really bad axis. I really don't like drawing on a tablet. There it is. So it looks like it's 0 at 0, it's positive when x is negative, it's positive when x is positive. So the only bad thing is 0. Domain equals all numbers but x equals 0. And one thing that I'll recommend you do is go back, grab your calculator, graph these preceding 4 functions using your calculator, read off the graph by looking at the graph on the calculator. I'll say don't use Wolfram Alpha for this because Wolfram Alpha will decide to give you like the real part and it'll make you think the domain is bigger than it is because, well, you can make sense of what the log base 2 of -1 is. It just happens to be complex. Nice. So, closing thing. Let's remember how to sketch graphs of functions. So let's try to sketch the graph of g of x equal to the ln of 2x plus 1 minus 1. Let's remember the order that you're supposed to do graphing like this in. So, first you should go down 1, then you should go left 1. So, let's do that. So, I'll trace these 2 points first. Oh dear. Oh, it sounds like it's, well, time to go to class, I guess. Very good. So let's move these 2 points. So this point at 1, 0 will go down 1, left 1, become the point at 0, negative 1. This point at E, comma 1 will go down 1 and left 1, and wind up at, well, E minus 1, comma 0. This vertical asymptote will go down 1. That won't move the vertical asymptote. Moving a vertical line down doesn't change it. And it'll go left 1. The overall graph will look something like that, without that weird bendy bit in the middle. I'm really bad at drawing on tablet. Nice. Cool. So remember all the things that you knew previously, and now apply them to these new functions. All right, I will stop here, and I will attempt to post everything. And hopefully later on today, I'll also post solutions to the homework problems that will be assigned today. Great. Enjoy your social distancing. Talk to you when I talk to you.